Hi there, welcome to this video. My name's John, and in this video we're going to take a look at the inverse trigonometric functions. I've decided to make a video on inverse trigonometric functions because it does seem to be something that a lot of A-level maths students really have some serious difficulties understanding. And in my experience, there are several reasons that are the cause of these difficulties, some of which I'm going to mention briefly, although I'm not going to go into detail addressing all of those underlying problems in this particular video. I'm going to mention them, and if you would like me to make any videos going forward, going into more detail with these particular topics or whatever, just let me know. Okay, so one of the main problems that people have is that they don't really have a sufficiently thorough grasp of what we mean by a function in mathematics. Now, a function is it's not the easiest thing to define. I'm not even sure that mathematicians necessarily go so far as to try to define a function. I think it's often taken as kind of a primitive concept, although it can be explained what a function is. I'm not going to get into that in this video, but you need to have a good enough grasp of what is meant by a function. You need to understand things like domain and range of a function. You need to understand that there are different types of functions, one-to-one, many-to-one, and that some functions, but not all functions, have an inverse. You need to know things like under what conditions does a function have an inverse? If not all functions have an inverse, when does a function have an inverse? Okay, you need to understand things like this, and to really get the benefit of the contents of this video, you'll need to have a reasonably good understanding of those things. So if you're not familiar with those ideas, I would recommend that you spend a bit of time familiarizing yourself with those notions before you take on this video. Okay. Another problem that people have is that when it comes to inverse trigonometric functions is that they're just not familiar with the normal trigonometric functions, sine, cos, and tan. I'm not going to get into sec, cosec, and cot in this video. It's really going to be limited to sine, cos, and tan. But there seems to be a lot of resistance when it comes to learning, for example, the graphs of trigonometric functions, which to me are an essential thing to know when it comes to trying to understand trigonometric functions. And unfortunately, there are many things if you take the typical classroom approach to teaching A-level maths, typical A-level maths textbook, there are many obstacles, and it's bewildering to me why this is the case, but it is. There are many obstacles that are put in your way to prevent you from understanding trigonometric functions. And I think these obstacles are, they're not necessarily meant to be obstacles, they're well meant, but unfortunately they do prevent you from really, or discourage you from really arriving at a good enough understanding of trigonometric functions. And one of those things, one of the most pernicious techniques that you will come across at A-level in the classroom, in your textbooks, is the cast diagram. Okay, the best advice that I could give you is, if you've had this foisted on you, the cast diagram, ditch it as quickly as you can. If you want to have any hope of understanding trigonometric functions, ditch the whole cast diagram approach. Cast diagrams are an awful technique, in my opinion. I'm not saying that actually they don't work. They do work in a certain sense. If you just follow the steps dictated to you when it comes to the cast diagram approach to solving trigonometric equations, yeah, you'll get the solution, but you won't really understand why the solution is the solution. You won't really understand why these other solutions are actually solutions to that trigonometric equation. And if you've got multiple angles involved and things like this, cast diagrams become awful. I just cannot recommend them in any way, shape, or form. Okay, it'd be much better for you to learn to work with the the graphs of the trigonometric functions, and that is what I always personally encourage my students to go for. They don't always listen to me, but that's what I always encourage them to do. I never encourage cast diagrams. So let's have a look at, and by the way, if I was to ask you to sketch the graph of, let's say, y equals sine x between 0 and 2 pi, or between 0 and 360 degrees, if it takes you more than a few seconds to do this, 10 seconds maybe, then you're not familiar enough with the graph of that function, sine x. Get it sorted. That's all I can say. If you have a tendency to mix up the graphs of sine and cos, that's a big clue that you are not familiar enough with the functions sine and cos. Okay, for me personally, it's inconceivable that I would mix up the graphs of y equals sine x and y equals cos x. And I'm not trying to brag or anything like that, because it's nothing to brag about. But it is something. If you mix these up, if you get them mixed up, you confuse them with each other, it's a sure sign that you're not familiar enough with those concepts. Again, all I can say is get it sorted, really, because it's going to hold you back. So let's have a look at the graph of y equals sine x. Okay. So we're only after a sketch of the graph of this, so it doesn't need to be perfect. It's definitely not going to be perfect, I can tell you that for certain. So it's going to look something like this, between minus pi, 0, pi, 1, minus 1. Okay, let's stick in pi by 2 as well. Pi by 2 and minus pi by 2. And the graph is going to continue. It's going to oscillate. It's 2 pi periodic, so it repeats itself every 2 pi radians. And I am going to be using radians in this video, not degrees. We need to get used to using radians. That's the... Going forward with advanced mathematics, higher level mathematics, you will need to use radians, not degrees. Okay, so I'm going to continue this. So that goes up to 2 pi. In fact, I'll tell you what, actually, I will actually draw it in as a solid line. So 3 pi by 2. And, okay, it does go in the other direction as well, indefinitely. But I'm not going to necessarily draw it all in. Okay, so we've got something like that. So, one thing to notice, straight off the bat, with y equals sine x, it's not, and I emphasize not, 1-to-1. It's not a 1-to-1 function. And we can see this if we choose any y value between and including 1 and minus 1, and we draw a horizontal line at that value, we can see that we've got many values of x that will correspond to that y value. Okay. Remember, the graph continues indefinitely in either direction. We're going to get an infinite number of values of x that correspond to that y value. Okay, so I've drawn a few there on the screen. So we've got one here, we've got one here, we've got one here. There'll be some down here somewhere. Another one up here. There's an infinite number of them, right? So the function is not 1-to-1. So what does that tell us? It don't have an inverse. So no inverse. But hang on a second. How can I make a video on the inverse trigonometric functions if I've just said that y equals sine x has no inverse? And the answer to that is that we can talk about inverse functions of sine x, but we need to make some suitable restrictions to our function. Okay? Particularly to the domain of our function. Now, there's many different ways that we can do this. There's all sorts of ways. But we want to restrict our function y equals sine x to some interval on the x-axis where it is 1 to 1. In addition to that, we would like the interval that we restrict to, we'd like it to be kind of maximal in a certain sense. Okay, so for example, we could restrict between the values of x between 0 and pi by 2, including 0 and pi by 2. And in that range, the function y equals sine x is 1 to 1. Okay, it's 1 to 1. But it's not maximal. Okay, because if I extend, if I restrict from minus pi by 2 to pi by 2, the function is still 1 to 1. But if I extend any further beyond minus pi by 2 or pi by 2, then the function ceases to be 1 to 1. Okay, so in a sense, this interval minus pi by 2 to pi by 2, if I restrict sine x between those values, the function is 1 to 1, but it's kind of maximal, because if I go any further, then the restriction is not sufficient to make the function a 1 to 1 function. So if I restrict, then restrict y equals sine x to a domain minus pi by 2 to pi by 2, so that's the closed interval minus pi by 2 to pi by 2, then this is 1 to 1. And in this case, we have an inverse function. Okay? A lot of people really struggle with this because they're just not familiar enough with functions, inverse functions, domain, range, 1 to 1, and so on and so forth. Okay? This is why to really understand inverse trigonometric functions, you have to make sure that you've got a grasp of these terms. Okay? So, as you may already be aware from your GCSE work, or maybe if you've come across it at A level, if you know what the graph of if a function has an inverse, it's 1 to 1, so it's got an inverse, and you know what the graph of the function looks like, then you can figure out what the graph of the inverse function looks like by reflecting the graph in of the function in the line y equals x. Okay, so I do plan to make a video on inverse functions at some point. So watch this space. So I'm going to go into more detail in that video, if I get round to making it, to show how inverse functions work and some of their properties. But let's just go back to our graph of sine x with the restriction applied. So we've got something that kind of looks like this. Oh, that's not very well drawn, is it? Really want it to go through the origin. Oh, third time's lucky. Third time's a charm, right? It'll do. So we've got something that looks like that. More or less. Minus pi by 2, 0, pi by 2, minus 1, 1. So this is y equals sine x with the restriction. Okay? So if I reflect this in the line y equals x, what will it look like? So you've got to use your imagination a little bit here. Visualize it in your mind. But if we take any point on the graph of y equals sine x, just a point here, and it's got coordinates a and b, then if we reflect this point in the line y equals x, this point will end up at the point with coordinates BA. Okay, so the point with coordinates AB will end up at the point with coordinates BA. Okay, so the x and y coordinates of the original points on the graph of the original function will just switch around. the x-coordinate becomes the y-coordinate on the new graph, and the y-coordinate on the original graph becomes the x-coordinate on the new graph. And this happens for all points. So what we end up with is something that looks like this. Okay, so this will be -1, this will be 1. It'll go up to pi by 2, and it will go down to minus pi by 2. Okay. So, bearing in mind that when we talk about a function f, which is invertible, in other words, it has an inverse function, how do we talk about its inverse function? We'd call it f with a little -1 there, right? F inverse. So if our function is sine, then it makes sense for us to refer to our inverse function as sine with a little -1 there. Okay, so this is the graph of y equals inverse sine of x. And another way that this might be written, because we don't have to refer to our inverse function like this. For example, if we've got the function x cubed, how would we refer to the inverse function of this? We'd use the cube root of x. Okay, so we don't have to use the little -1. Sometimes you will see arcsine x used to represent the inverse function. Okay. Now, actually, I'm talking about the inverse function, and this is not quite right because there are an infinite number of inverse functions that we could possibly choose from. It's just that this inverse function is the most common inverse function that we will be talking about when it comes to sine. Nevertheless, there are other inverse functions that we need to acknowledge, and we will use from time to time. Okay, we will make use of them. And I'll give an idea about how that works. So, actually, let's go back to the graph of sine x that I drew before. We made the restriction of sine x between minus pi by 2 and pi by 2. But we could also restrict, so let me just change the colour of my pen here. If instead we restrict from, let's say, pi by 2 to 3 pi by 2, then on this restriction, our graph of sine x is also 1-to-1. And it's kind of a maximal restriction that we've made, in the sense that if we were to extend beyond pi by 2 or 3 pi by 2 in either direction, the function, that restriction would not be sufficient for the function to be 1-to-1. But this is a perfectly good restriction that we could have for sine x. And this would give us a different inverse function for sine. Let's see how that would look. So, bearing in mind that this is the graph of the inverse function that when we restrict to minus pi by 2 to pi by 2, how about when we restrict from pi by 2 to 3 pi by 2? What will we get? What will it look like? It will look a bit different. So, okay, we're going to have pi by 2 here. And then the graph is going to look something like this. Oh, that's not very well drawn. It will look something like that. So this is 1. This is minus 1. This is 3 pi by 2. And this is pi. So compare that with the graph of what we had before. If I can get them both on the screen. So before, with the restriction between minus pi by 2 to pi by 2, we got a graph that looks like this. It starts down here and it goes up like that. However, when we make a different restriction... Oh, didn't want to do that. I knew it was going to do that. Right, let's get back to it. Okay. If we make a different restriction, then we get a graph that looks like the one here, which kind of starts down here, and it goes up in this way, and we end up at this point here. Okay. And we could make a restriction from 3 pi by 2 to 5 pi by 2, in which case we'd get a graph that kind of looks like the original one that we had, except rather than going from minus pi by 2 on the y-axis to pi by 2, it'd go from 3 pi by 2 to 5 pi by 2. And we could go in the other direction, from minus 3 pi by 2 to minus pi by 2, or minus 5 pi by 2 to minus 3 pi by 2. So we've got an infinite number of possible inverses. It's just that this one, where the restriction is from minus pi by 2 to pi by 2, is the most common. Okay, I think sometimes it might be referred to as kind of the principal branch or the principal inverse of sine. You might come across something like that. But this inverse from minus pi by 2 to pi by 2 is the inverse that your calculator will typically be programmed with. So whenever you are asked to let's say you do get this in your textbook from time to time. Evaluate, for example, inverse sine or arc sine or whatever, inverse sine of root 2 over 2. The answer to this would be unambiguously pi by 4. Okay. Similarly, if you were asked to find, and I'll use arc sine this time, arc sine of minus 1, the answer would be unambiguously minus pi by 2. Okay. On the other hand, if I asked you to solve the equation sine pi by 4, sorry, not sine pi by 4, sine x equals root 2 over 2, and I gave this in the range, let's say 0 less than or equal to x is less than or equal to 2 pi, there would be two solutions to this, pi by 4 and 3 pi by 4. Because when I rearrange this equation, so to speak, the sine x equals root 2 over 2, I don't just get necessarily this, x equals inverse sine of root 2 over 2. Because these are not equivalent. When we rearrange an equation, really what we're wanting to do is to rearrange that equation into an equivalent form. But these are not equivalent. Sine x equals root 2 over 2 and x equals inverse sine of root 2 over 2. These are not equivalent expressions. Because there are two values of x which solve this equation, sine x equals root 2 over 2. They're pi by 4 and 3 pi by 4. But once I bring inverse sine in, I've got a restriction there. Generally between minus pi by 2 and pi by 2. In which case, this is going to be pi by 4. I've missed the solution off. Well, that is unless I decide to go to a different inverse. So your calculator, remember, is programmed typically with that principal inverse from minus pi by 2 to pi by 2. But now, you've got to think, I mean, you can think about it in different ways, but one way that you might think about it is, okay, I'm going to change to a different inverse. Rather than thinking about that inverse from minus pi by 2 to pi by 2, I'm going to think about another inverse from pi by 2 to 3 pi by 2. In which case, pi by 4 would not be my solution here. It would be 3 pi by 4. Okay. So it's kind of clumsy to replace this equation sine x equals root 2 over 2 with x equals inverse sine of root 2 over 2. And this is another way that people can kind of get tangled up, because they don't necessarily appreciate that those two expressions are not equivalent. In the same way that if I've got the equation x squared equals 4, this is not the same as saying that x equals the positive square root of 4. These are not the same. The x equals the positive square root of 4 is one of the solutions to x squared equals 4, but there's also another solution, x equals minus the square root of 4. So it depends which restriction I'm placing on the original function of x squared. If I restrict to positive values of x, then this, and talk about the inverse function of x squared, which is the square root of x, then x equals the square root of 4 is the corresponding solution. But if I'm talking about the inverse corresponding to the negative values of x, which is minus the square root of x, then I get the solution x equals minus the square root of 4. Okay? So you've got to be very careful when it comes to inverse functions, not just inverse trigonometric functions, but inverse functions in general. But generally, when I see, for example, arc sine, y equals arc sine x, what I will generally understand by this is that principal branch. Okay? When I see something like y equals inverse sine of x, then usually I will understand that as meaning the principal branch, unless the context tells me otherwise. But arc sine x usually is reserved for that principal branch. Usually. I'm not going to say it's always, but usually. Okay? So you've really got to be able to read the situation when it comes to these inverse functions. So, for example, if we've got the function, I mean, this is going a bit off topic now, but if we do have the function y equals x squared, maybe I should write it as f of x. F of x equals x squared, which is a function from the positive real numbers to r, let's say. Actually, it would be from positive real numbers to positive real numbers as well. So that's what this symbol means, just positive real numbers. Then the inverse of this, f inverse of x, is equal to the positive square root of x. However, if on the other hand we had f of x, in fact I'll just change this. F of x is x squared from negative. Oh, shouldn't have changed that one, should I? From negative real numbers, or 0, to positive real numbers. The inverse function is minus the square root of x. So you've really got to be able to read the situation. Okay. So let's have a look at cos. Similar things apply to cos. So if we've got y equals cos x, what does the graph of cos x look like? Something like this. So that's minus pi by 2, minus pi, 0, pi by 2, pi, minus 1, 1. And of course it continues indefinitely. So in this case, again, the function is not one-to-one. It doesn't have an inverse, unless we make a suitable restriction. But we can't restrict to minus pi by 2 to pi by 2 in this case. For if we do, our function is not one-to-one. As you can see from the diagram. Choose a y value, it's going to have more than one. Why did I draw that there for? It's going to have more than one corresponding x value. It's not 1 to 1. However, if I restrict from 0 to pi, then my function is going to be 1 to 1. And it's going to be kind of maximal, again, in the sense that if I extend either way, then the restriction will not be sufficient for me to ensure that the function will be 1 to 1. So, what does the inverse function look like? I say the inverse function, again, it's kind of a inverse function, or the principal branch, the principal inverse, however you want to refer to it. Actually, no, I should have drawn that further down. The graph of the principal inverse function is going to look something like, so let's have a look. Reflecting the line y equals x from 0, going from 0 to pi, we're going to get a graph that looks like, kind of like this. So 1, minus 1, 0, pi by 2, pi. And that's the graph of y equals, and it'll be written as cos with a little minus 1 x, or arc cos. Again, when I see arc cos, I understand the restriction as being from 0 to pi. When I see cos with a little minus 1, that to me means usually the restriction from 0 to pi, but it could mean some other restriction depending on the context, and you just have to read the context. Okay, but again, there are other restrictions that we could make. So we've restricted here from 0 to pi. We could restrict from pi to 2 pi, or from 2 pi to 3 pi, or from minus 2 pi to minus pi, or from minus pi to 0. And each of these will give a slightly different inverse. How about tan? Y equals tan x. Now this is one graph that so many people struggle with this one. It's it's unnecessary. So understand that minus pi by 2 and pi by 2, you've got asymptotes, vertical asymptotes, because the number of times I see people kind of draw tan and they'll just kind of draw it like this, and it just crashes straight through the asymptotes, and there's no real the asymptotes are not really properly represented in their diagram, and it really misleads them. This is nothing to do with necessarily getting marks on an exam. This is just you demonstrating to yourself that you understand this function and its behavior. So you've got the vertical asymptotes from minus pi by 2 to pi by 2, so it's unbounded on the y-axis, and it's pi periodic. So here we've got 3 pi by 2, so we're going to have another vertical asymptote there, and get something that looks like that, and it will continue indefinitely in either direction. Okay, so minus pi, and so on and so forth. Again, we see that tan is not 1 to 1, but it will be with a suitable restriction. What's the suitable restriction? In this case, it's the open interval. So it's similar to sine, but whereas with sine we restricted from minus pi by 2 to pi by 2 inclusive, so the closed interval, for tan it has to be the open interval. So it's minus pi by 2 to pi by 2, but not including the values minus pi by 2 to pi by 2, because tan is not defined at those values. So what does the graph of inverse tan look like? Again, I'm talking about the principal inverse. There are multiple inverses that we could select from. We could restrict from pi by 2 to 3 pi by 2, from 3 pi by 2 to 5 pi by 2, and so on and so forth. But the inverse of the principal branch is going to look something like the following. So we've got pi by 2 here. We've got minus pi by 2 here. 0. We're going to have horizontal asymptotes here. Oh, could have made a better job of that, couldn't I? Horizontal asymptotes. And the graph looks something like that. Okay, so this is the graph of y equals tan with a little minus 1 of x, or arctan of x. Okay, if we chose a different inverse, then we would get something that would look maybe something like this. You know, from pi by 2 to 3 pi by 2, and so on. And that's it. So that's how you can better understand, hopefully, inverse trigonometric functions. I'm not saying it's the only way. It's just there's a lot involved. Okay, there's a lot involved. Understanding why you have to make these restrictions, understanding what it means for a function to be one-to-one, and why that is relevant when it comes to a function being invertible. Okay, and the fact that you do have a choice of inverse functions, just as you do with the square function, y equals x squared. It's got two different inverses: square root of x minus the square root of x. Okay. And this is something that I've seen come up at GCSE, so it should be, if you've done your GCSE maths, it's something that you should already be familiar with in many ways. Because I have seen it come up on GCSE maths exams. And so you need to be able to understand it for A level. If you don't understand these things, make sure that you spend some time getting your head around them. Okay, so I'm not going to go any further with this video. If there is anything that you would like to ask in addition, please leave it in the comments section, or please get in touch. If you do want me to continue making these videos, please show your support for this channel by hitting the subscribe button and hitting the like button. I don't make any money from making these videos, and I'm not asking for any money for making these videos, but I can only really justify making them if there is sufficient demand for them. So if you do want me to continue making these videos and make them freely available to you, show your support for this channel. Share these videos with other people. Also, if you want to give me some constructive feedback about what I could be doing differently, I've got a certain idea about what I want this channel to be about, and there are some things that I definitely want to keep in my videos that I'm not willing to change, but that there are other things that I'm open to altering in future videos. If you've got anything that you think I could be doing better, things that I could be talking about that maybe myself and other A-level maths YouTubers are kind of missing, let me know. And if it's something that is not going to change the what I aim for this channel to be about, what I plan for this channel to be about, if it doesn't conflict with that, then I'll start to incorporate that into my videos. So I want these videos to help you as much as possible. I'm making these videos at the moment basically for me, as if I were doing my A-levels now. What kind of things, thinking back to when I did my A-levels, what kind of things would I be interested in learning about and understanding better? But I am not doing my A-levels right now. If you're doing your A-levels right now, I want to know what you need help with, and how I can better help you. So hit the subscribe button, hit the like button. If you made it this far into the video, congratulations. I'm going to leave the video there. Thank you very much for watching, and I will see you in the next video.